So we have this talk on coupling pencil and Eulag by Guilherme Monteiro. So Guilherme, please go ahead. So it's all yours and
Okay, thank you. Thank
30
you.
minutes.
Okay, thank you very much. My name is Guilherme. As I was saying previously, I'm a Brazilian PhD student, and I'm currently on NPS, doing what I'm going to show you now. That's the Pencil-Eulag coupling. So, as some sort of background and motivation of why we are doing it, during my PhD, I tried to understand how the magnetic field evolved or is presented in radiative zones. At first, because I am personally not so, how can I say this? I'm personally would like to better understand how the solar radiative zone affects its magnetic field. As far as I know, there are some simulations that include it, but most of them neglect this region. And I would like to understand better how it affects the magnetic field cycles. And secondly, there is a set of stars called APBP stars. They are stars of A and B type that are chemically peculiar, and most of their structure is radiative. And although that's the case, they do present some quite strong magnetic fields. And the origin and how they're maintained is not so well understood by literature. Of course, there are theories, but nothing uh, close yet. And so, when we think about magnetic fields, we come with the idea of dynamo that was read well explained several times during previous talks, but I would say just a little bit of it. And in dynamo, we normally would look for two main effects. The first one will be the omega effect that will twist the poloidal field lines into toroidal field lines. And the second one will be the alpha effect that will twist meridionally those lines once again into the toroidal lines, once again into a poloidal field component. If we look for the sun, the agents responsible for those effects are the differential rotation for the omega effect and the eddy movements and turbulent movements for the alpha effect. But if we try to mimic those effects on radiative zones, they're not so logical. I mean, you will not be able to see eddies on radiative zones. So how can you have some alpha effect occurring? Uh, 2 years ago, a couple of years ago, a paper from uh, from Schneider, 2019, from Nature, showed that they used the fact that APBP stars lack companions to try to understand if it would be possible for this chemical peculiarity or even the magnetic field to be from the origin of one star absorbing another. And when they did this in simulation, they found that although the structure of the APBP stars would be in their simulations would be radiative, uh, they would present differential rotation. And so it comes back with an idea that's been around for quite some time called Tyler-Spruit dynamo. This idea was presented at first in 1999 by Spruit, where he presented this theory where the dynamo could occur into a radiative zone. In his theory, the omega effect would be represented by a differential rotation in the radiative zone, while the alpha effect would be created or managed by the Tyler instability. For those who are not aware, Tyler has a series of works on the stability of magnetic fields into radiative zones from the late 70s to early 80s or something. And one of the main results that they got is that the toroidal fields are unstable in radiative zones. You will only be able to stretch its lifespan or even to make it stable in the using additional colloidal field components to stabilize the field or very strong rotation rates. And in this case, on the Tyler Sprue dynamo, what Sprue proposed was that the non-symmetric field generated by the stability would suffice to be rewinded by the to be represent a representation of colloidal field and rewinded into a toroidal field by the existing differential rotation. Across the years, several authors have addressed this. I would point here Braithwaite at first, and then Zhang of 2007. I think they are, if you are interested in this topic, they are good places to start and look for references. And so, uh, during my PhD, I did some tests on this kind of field. So we imposed on a spherical shell using the Euler code. We imposed a solar-like differential rotation, as this one that's shown here, and we did in two different cases. On the first case, we implemented a random field inside the simulation, inside the region, where this field would have a mean value of zero. It would be basically zero everywhere, but very small values. And by inputting the solar-like differential rotation, what we observed was that the field started to reorganize in itself and amplifying, and then displaying some dynamo-like characteristics, such as cycling, polar migration, and equatorial migration. We also tried to identify some sort of alpha effect that could be present in this data in this simulation, uh, and we found it, but we were unable to express it to determine uh, the real origin of this alpha effect that would complete the dynamo in this case, in where we were already forcing the solar differential rotation. And when we tried on the toroidal case, which would resemble much more the tile instability, uh, what happens was that at first the magnetic field would decay. So here in this case, we can see that the North Pole has a positive magnetic field, while the South Pole has a negative one. Both are basically Gaussian slabs of magnetic field in terms of distributing latitude, and and so as the differential rotation sets in, we see that the same effects that we seen previously also occur in this case. So we see although initially the field had decayed, it maintains somehow its intensity level, but starts to exchange in terms of polarity and migrates both equatorial wards and polar wards. And since we could not determine the origin of the alpha effects using only the data from Eulag, we trying to find an alternative. In this case, it was the pencil code. Pencil code has the test field method imputed on it, and the best case scenario for us was to couple the codes, then be able to access this tool by sending information. And the fluxogram that you see here is our basic idea of how it should work. So we would have a coupled execution that would call for both pencil and Eulag. After a brief handshake that would share some essential information between them, they would start running it separately, where Pencil would wait for some data from Eulag, and that after receiving the first steps, it will start to interpolate the data and generate the alpha coefficients for it. Later on, it will receive more data of the system evolved a little bit more and continue this interpolation. Meanwhile, for Eulag, it will simply do as it should, and once in a while send some data for Pencil, and that was it. Some things that we wanted for the codes to have or to be independent. So we alter the codes so that if we had a coupled experiment or a couple test, it will recognize, okay, there is another code running beside me, and I'll have to address it. But if there was no other code, it will simply run as it would usually do, without any alteration, without any major change. Uh, we also look at for processor usage efficient, which means that none of the codes would be idling, waiting for the other to give any response or to do anything else. They would try to maintain these time rates uh, close together. It was also essentially that the reinitialization capabilities of both codes would be on par of it. So normally the Euler code, the fields on Euler code would take longer for it to develop. And since we want to make a good use of resources, we could run Euler separately until it reaches this stable phase, or until the fields are stabilized, and then access the coupling so that from that point on, Pencil would start to generate the alpha coefficients. And this is also good because we can, let's say, reinitialize the code at some point and try to figure out the coefficients for that region specifically, if we don't want to run all the length. Something that needs to be said is that you have to, if you want to do something like this, or if you want to use even our sample that's already inside the Pencil repository, you have to be aware of the machine that you are using. Both Eulag and Pencil has some pre-setups uh, that are done by directing to the machines, and in case of which compilers, which modules, and which executables to be used. And you have to make sure that in both codes they are running on the same page. Otherwise, you can have quite a big problem even to identify what's happening in those cases. So as for the coupling initialization, the pencil is already implemented in itself. Matthias did this. So if you run if you inside your bash, or however you run your executional, you place the run.csh with an additional information, in this case, n minus np, which gives the number of processors that Eulag will be using, and the Eulag executable. The pencil would immediately identify that there is a companion there is a foreign code, and it will access the whole branch of foreign communication. It's important to say here that the total of processors used in this case here, it's the number of processors that you have already set up for Eulag, for Pencil, sorry, plus the ones you are setting up for Eulag. In this case, the ones we set in run.in, I think, uh, they will be added by this one. They are not shared. And this is important because the initialization of MPI, of the MPI or parallelization in both codes, they are basically done like this. This is common for both of them. And what it does normally, if the code is run alone, is that the MPI control would communicate with all the available processors. In this case, it does communicate with all the available processors, but not both codes will be able to access them. So to guarantee that this is what happened, we need to add these three more lines, where the first one will identify which of the programs are using with which of the codes we are using. The second one will split the global com, the world com, into local coms. In this case, for Pencil, MPI com Pencil. Uh, and for the case that in the case that we want the code to run independently of the coupling, we have to change all of the occurrences of MPI com world in the original code by the local one. So if we do this, if we change correctly, what happens if you run, for instance, Eulag alone, the MPI-com world and MPI-com Eulag would point to the same place. So it will run normally, And in the case that you have the pencil by its side, the MPI con OILAG will only be directed to the processors that are responsible for OILAG. And this is just troublesome, but is easily done. During the handshake, it's important to say that to avoid waste here, we use only the root processor in this case. Normally, it's sufficient to most of the informations that we want to share between the two codes. Once in a while, some informations need to be extended to the other processors of that code, and then we use a local broadcast simply to do so. Uh, in this case, we also confirm the couple integrity, which means check on the current state for the coupling, for instance. Both codes need to have the same number of processors in theta and phi. This is important, and need to check this and other minor changes that might occur. For the R direction in this case, on our case, the OILAG doesn't have a parallelization in R, different from Pencil, which has. And to try to improve the rates into which the codes communicate, we were able to apply a mismatch clause on the Pencil side that will allow us to implement more processors in the X than OILAG has. OILAG basically has one. I will address this a little bit later. Other things that are important in this communication is the units. OILAG uses SI units while Pencil uses its own. So it's important for you to determine which units you are using so that Pencil can renormalize the data when it comes. So it says, okay, I have a renormalization factor for velocities. I'm receiving velocities now. I will renormalize the data or time or whatever. And this is all done in the handshake. It's quite fast. It doesn't take a minute to do this all this exchange of information. And other thing is the peer determination is also done here, and what we call peer determination. So if you are sharing the data, actual data in both cases, we can see here a very simple uh, draw of how the codes work. So on OILAG, the structure is is structured as phi, theta, and r, while Pencil is structured as r, theta, and phi. This means in practice that in this case that you have two processors both in phi and theta, the structure of the processors will be like this in both cases. So we had to redistribute the data. We have two options. The easiest option to share the data is to take the data from all the local processors into the root, and then share the data root to root, and then inside the Pencil code we would distribute this data. This is by far the easiest way to do it, and also the slowest one. So what we did, we using the local communicators and this peer determination, we could address, okay, so the data from processor 2 of OILAG needs to go for processor 1 of Pencil, and so on and so forth. And this we can fastly distribute the data all together. So it's instead of four movements like this, basically, we have to send for root to, no, actually three. Root all to root, and root to everyone else. Here we're doing only one, basically. And this is one of the most important parts of what we have done. And since I've said that we were able to extend the Pencil code so that it could use more than only one processor in the X direction. This becomes this the determination of peers becomes a little bit harder, because now on every processor of OILAG, it has to send, in this case that Pencil has two processors in the I direction. Every processor of OILAG will have two addresses to send data. And so that's why the handshake is such an important part of this, because it's there that we identify the number of processors the grid size and the domain that it englobes, and how this data is going to be distributed. So so far we have been able to do this kind of distribution up to 16, yes, 16 processors in the X direction of pencil side, and using two and two. That's what we have been able to test. We are already testing to a higher grid simulation, but in the 64 cases it worked perfectly. It's also important to address why we do it, because for our surprise, the time efficiency of this coupling is not doing so well. The pencil takes much more time to process the the test field method than OILAC takes to send the new data. So it's mandatory for us basically that we increase the number of processors that Pencil is allowed to use. So then we can have this time efficiency, get a better time efficiency of the processors that we are using. So in conclusion, now we are able to efficiently send the data. Uh, this is done. Uh, we we also can increment the pencil side, the number of processors in the pencil side, but we still have to do more, and that's is going to be on our next steps, is to implement additional processors for pencil in the Y and Z. And the two main difficulties that we are having and we will have, the first one is uh, to address the numerical diffusivity problem. To do the test field method, the pencil code it also influences the time efficiency of the coupling. To do the test field method, the pencil uses numerical diffusivity, and OILAG uses sorry, the pencil uses diffusivity, and for OILAG, this diffusivity is numerical, and we cannot determine it on the fly. We will have to figure out a way to do so, but so far we are unable to do it, and we are doing by hand. And as far as tests go, it's okay. But if you want to a better production, it has to be better determined. It's interesting that since we can reinitialize the data, we can reinitialize the coupling or the codes, we have a way to post processing, uh, try to determine this numerical diffusivity. And since we can reinitialize, this is probably a way to go at first, to stop the code, determine the numerical diffusivity or the effective diffusivity of the system, plug it back and run it again. That's one of the ways to do it, more troublesome, but it can be done like this. The second problem that we have is the grid difference. Pencil does not simulate the poles, and OILAC does. And this is something that we still have to address. So far, what we are using is simply stuck the data into the pencil grid, and that's how we are doing that. But we are probably going to have to do a better distribution of this data later on. But as far as it goes, this is the state of the company so far. I think there's it. Thank you very much.
Thanks a
Michael,
lot, Guillermo. It was a really nice talk about coupling these two codes. Must be a lot of hard work, but I already see two hands. Axel, you want to go first? Unmute and ask your question.
Yes, yeah, thanks for absolutely amazing developments that you're doing here. I was wondering about the inelastic versus compressible. So the equations also are not really quite the same in that respect, isn't that right?
That's true. That's true. But I don't see that as a problem, since what all we pass for the pencil side is the velocity fields. And as long as the velocity fields are recognizable, I don't see why the compressibility of the code
Oh, I
is.
see, because you don't have the induction, you don't have the momentum equation, just the induction equation, right? Yes, of
Yes.
course. Yeah, exactly. Mhm.
Jorn, you want to go next?
Yeah, I just have a short question. So when you said that the pencil takes longer to compute, is this the issue of the numerics or is the issue of the time step?
I think it's the issue of the time step. Not I think. The issue is of the time step. We cannot increase the pencil time step so much.
So you're limited by which time step? By the sound speed or what?
Oh no, it must be the velocity, not the sound speed.
Yeah,
but in
normally for the-
Eulag is implicit. Is that right? It's not just inelastic; it's actually implicit.
The velocity, the sound is inelastic. There's no.
Nobody. The induction equation in Eulag, is that solved implicitly or is that explicit? Because then I would not understand why the time step can be longer for Eulag.
Okay, so let me try to understand the question. Sorry.
I mean, normally the time step has to do with delta x divided by u. That
yes,
has
no,
the units of
the time step in Eulag is explicit.
Yeah, so then the time steps should be comparable both for Eulag and for the pencil.
But the problem is that because sorry, I don't know which parameter is exactly, but when we compute the alpha coefficients, there is a dt that we cannot increase it tremendously, and I don't know why. It changes if we change the CDT on the run, and it changes if we change the diffusivity, but we cannot if we change it too much, everything goes.
And I mean, if you solve
not stable.
on the pencil code side, you basically only solve for the induction equation, or not, and the test fields. The
It's just
test
a
fields
test field.
are kind of induction equation. So
Yes.
then I would say then the only time step is the Alfvén time step.
Sorry?
It's the Alfvén time step. Alfvénic
But
time
there's
step.
no, but there's no density in the induction equation.
Yeah, that's true. That's true. Okay.
That's the, and then we are limited by it. That's the problem. And we can, if we can increase the number of processors, that will be fine. But I don't see. I mean, maybe there's some other technical changes that we can do. We tried to change the CDT and the everything else, but if we do,
Yeah, but first you should check what is your limiting time step, and then see what you can do about it.
Yes, so far is in pencil units, the biggest time step we were able to get was 7 to the -3, and but every day if we send data from Eulag at every time step, it will be 5.8. But 5.8, not 5.8 to the minus anything, just 5.8. So this takes too long for the pencil to reach. For instance, half an hour is not sufficient. And if we are using 16 processors in the pencil side, in the X of pencil. That's.
So it should be it should be possible to calculate how much of the time it is spent in the communication and in. I think you are using the test field module, if I understand correctly, right?
Yes.
So
We are using.
there must be some way to calculate how much time this code is spending in getting the velocity from the Eulag and then to calculate this, right?
Yeah, but the time for it is basically negligible because of the way we distribute the data. It's a simple numerical distribution, so everything goes at the same time. The problem that we have is if, for instance, both codes do not reach on the same time the time frame that they should communicate. And then if we are in a blocking case, I don't know, maybe I should have explained this on the code. There's two types of communicate. This communication can occur in two ways. The first one is blocking, where if some of these processes do not receive the data, it will hang. This is the first one. The second one is non-blocking, where the sending will simply send and continue going forwards, and the layer would be waiting for some data to arrive. At the beginning of the communications, we do blocking so that it will wait for the data to arrive, and then both codes move forward. But onwards, we intend to do so that Eulag can simply keep sending the data, and as Pencil catch up, it will simply do the analysis forward. So the time of the sending itself is pretty negligible in this case. It takes much more on the Pencil to arrive at the point that it has to receive. It takes infinitely more than for the message to be sent onwards. Of course, it degrades the efficiency of the code if they are working alone or together, but that's it. That's not by much. That's what I'm saying.
So doing it in real time, you are saying, is much better than, say, doing it in post processing, or when you take the EULAG data and then later on use the pencil code to that. So,
yes, but I think it's not possible to do so. We have I think I have had this conversation with Matthias before, but I don't think it's possible to post-processing the Eulag data into, because, why? Okay, he explained to me and I forgot, sorry for this. But
I mean, the thing is, you need a lot of data. You need a very high cadence because
each
you have
time
to
step.
solve an
Each
evolution
time step.
equation.
So he's taking each time step, right?
Yes.
But ideally, we would not like that. We would like a more spaced frame rate or exchange rate. But for now, we are doing it every time step.
I
But
think
the test field would work for only a few. If you take only a few time steps, then wouldn't the test field work? Because it is not a evolution. I mean, if you take the saturated stage or something.
Yeah, but even then, you need actually, if you want to do time average coefficients, you need actually you have to evolve for a long time. So in the saturation state, and then you need a high cadence of output. Because you have lots of random noise on top. So you have to have a lot of sampling to actually average over this. So that's so I don't think that would be, I mean, theoretically one be possible in post-processing, but then the Eulag has to write out, I don't know, maybe every 10th or every at least 100 time step it has to write out a snapshot or the velocity file. That's not handleable, I think. That's the problem.
Yeah, I was thinking only if it is only a few time steps, then it should be easier to do post-processing.
I still had a question about the time steps.
Okay.
So you said that if I understood correctly, there is like a factor of 1,000 between the time steps from Eulag and then pencil code.
Yes.
But are these in the same units?
No, they're units.
So that's the point.
No, sorry. They are in the same units. They are in pencil units. Yes, they are in pencil units. So for pencil, it recognizes, it receives, in the best case scenario, every Eulag data every 5.8 pencil units, whatever that is. But every
but the pencil unit is the freefall time, I think.
Sorry.
The pencil code time units is usually the freefall time.
Yes, true. That's true.
That is just the induction equation.
What is the freefall time in your simulation?
Yes,
Petri, I thought the pencil code wouldn't actually solve hydrodynamics. Just the induction, just the test field method, I thought.
Right.
But but we actually passed the free fall time. We had to calculate it, and during the handshake we passed it through for the pencil side. Yes.
Okay.
And that's a factor of basically yes, 1,000.
Okay, yeah, need to think about this a bit more.
Matthias is also online. Do you understand why the time steps are so completely different? Matthias?
Yeah, but what the time unit is on the pencil side, it's practically undefined. No,
But it must depend on the velocity. With the velocity is very...
Yeah, but then...
also diffusion, by the way.
The time step chosen is by the time step control on the pencil side. So what the time unit is, it's up to us in a sense.
Okay, but maybe that's not even correctly calculated.
Okay.